All right, let's jump right in. Today, we are going to decode a powerful secret language, one that data scientists use to make sense of our incredibly messy world. Welcome to our guide on Principal Component Analysis, or PCA. So, to get started, I want you to just think about this question for a second. You've got facial recognition, you've got financial modeling, you've got image compression. I mean, these are completely different worlds, right? So what on earth could possibly tie them all together? Well, the answer is actually pretty simple, but it's also really profound. Every single one of them, deep down, is trying to solve the exact same problem. They're trying to find that one meaningful pattern, the signal, that's buried inside an absolute ocean of meaningless data, the noise. And that, right there, is one of the biggest challenges we face in the modern world. It's the problem of having, well, just too much. You know, we live in this age of big data. But here's the thing, more isn't always better. When you're dealing with hundreds, maybe even thousands of different variables, or dimensions as they're called, you slam right into what data scientists call the curse of dimensionality. Your data just gets unwieldy. It's noisy, it's slow to work with, and worst of all, the actual story, the thing you're looking for, gets totally lost in all the static.
So how do you fight that curse, right? How do you simplify things without just throwing away all the important bits? Well, that brings us to the hero of our story today, and what I like to call the art of simplification.
Meet Principal Component Analysis, or PCA for short. At its core, it's a brilliant technique that takes all of those messy, confusing variables and basically squishes them down into just a handful of new, supercharged variables. We call these principal components. And the real magic here is that it manages to do all this while keeping as much of the original, important information as possible. Okay, so to really get this, I want you to hang on to one big idea for this whole explainer. Think of PCA as a kind of data cartography. We're not getting rid of the landscape, not at all. We're just creating a better, simpler, more useful map of it. You know, a map that shows you the main highways instead of every single little side street and back alley. So, if we're going to be map makers, what's the first step? Well, you've got to survey the terrain, right? You need to understand how everything in your landscape relates to everything else. It's time to start mapping our data's patterns. And the very first tool we're going to pull out of our map-making kit is something called Covariance. Now, don't let the name scare you. It's a wonderfully simple idea. It's really just a number, a score, that tells you how much two things tend to change together.
Now, yeah, you see a formula up here, but let's just ignore that for a second and focus on the intuition. All this is really asking is a simple question. When one of my variables zigs, does the other one tend to zig with it, or does it zag and go in the opposite direction? That's it. Covariance just gives us a score for that relationship.
And it basically comes in two flavors. You can have a positive covariance, which means that as one thing goes up, the other thing tends to go up too. Think about height and shoe size, right? And then you've got negative covariance, which is the opposite. As one thing goes up, the other tends to go down. Like say, the more you practice, the fewer mistakes you make.
Okay, so what happens when you calculate that little score for every single possible pair of variables in your whole data set? Well, you get something called the covariance matrix. And this is our master cheat sheet. It's the complete survey of our data terrain, summarizing every single relationship, all in one handy grid.
So we've got our survey map, which is great, but it's still way too detailed. It's got every little bump and dip. To make this map really useful, we need to find the main routes through all that data. We need to find the hidden highways.
And this brings us to the most important question of all. We've got this complex web of relationships in our matrix. So how in the world do we figure out the most important directions? The main roads that are carrying most of the traffic?
The answer, it turns out, lies in this really cool mathematical idea involving eigenvectors and eigenvalues. Now, the equation might look a little intimidating, but the concept behind it is, wow, just think of an eigenvector as a special direction in your data, kind of like its true north. It's a direction that doesn't change its pointing, even when you stretch and squish the data around it.
So here's the absolute key takeaway. The eigenvectors of our covariance matrix, they point in the directions where our data varies the most. They are literally the hidden highways we've been searching for this whole time. They show us the most significant, the most fundamental patterns in our entire data set.
But of course, not all highways are created equal, are they? Some are massive 8-lane interstates, while others are just quiet country roads. That's where eigenvalues come into play. See, for every eigenvector, for every highway, there's a corresponding eigenvalue. And that number simply tells you how important that highway is, how much data traffic or variance it's actually carrying. Okay, so now we have all of our map-making tools. We have our survey, the covariance matrix. We found the hidden highways, the eigenvectors, and we know how important they are thanks to the eigenvalues. Now it's time to put it all together and finally see the world through the lens of PCA. And the whole process really boils down to these 5 elegant steps. First, you get your data ready. Second, you build that relationship map, our covariance matrix. Third, you find the hidden highways by calculating the eigenvectors. Fourth, and this is the crucial part, you look at the eigenvalues and you decide to keep only the busiest highways, the ones carrying the most traffic. And finally, step 5, you create your brand new, simple map by projecting all of your original data onto just those few main roads. And the results of doing this, they can be absolutely stunning. Take a look at this. You could use PCA to take a crazy dataset with 100 different features and boil it all the way down to just 10. And here's the amazing part. You could do that while still holding on to 95% of the important information. That's how powerful this is.
And like we said at the very beginning, this isn't some abstract theory. PCA is a total workhorse. It's used everywhere, for data visualization, for cutting noise out of signals, for machine learning, for finance, for compressing images, even for helping computers understand human language. It's truly fundamental.
So in the end, you see, PCA is really more than just a math technique. It's a way of thinking. It's a reminder that even in the most complex, overwhelming, noisy systems, there are often a few simple, essential patterns just waiting to be found. And that leaves us with one final question for you to think about. What essential truths are hiding in your complex world?